They call it a comet, a frozen wanderer from the void, but this thing defies every rule we wrote about how comets work. Scientists at NASA just confirmed it, racing through our solar system at 245,000 kilometers per hour. Third interstellar object ever spotted. 16-hour spin, carbon dioxide fog so thick it chokes out water, and numbers that make astronomers question if they read the instruments wrong. What makes this rock from alien space violate the physics we trust? Why does it carry chemistry we've never seen before? What secrets does its ancient ice hide about a star system billions of years gone? July 1st, 2025, Rio Hurtado, Chile. The Atlas Telescope, Asteroid Terrestrial Impact Last Alert System, sweeps the southern sky like it does every night. 4 telescopes total across the globe, 2 in Hawaii, 1 in Chile, 1 in South Africa. Hunting rocks that could hit Earth. Larry Deno reviews the overnight data at the University of Hawaii. Moving object, strange trajectory. He sends the coordinates to the minor planet's center. By 1 a.m., Marco Micheli at the European Southern Observatory and Davide Farnocchia at NASA's Jet Propulsion Laboratory confirm what the numbers scream: hyperbolic orbit. This object came from interstellar space. Daryl Seligman at Michigan State gets the emails. He bolts awake. Sends messages worldwide. Turn your telescopes now. Within hours, 31 observatories lock onto the target. 122 observations logged. The Minor Planet Center announces it July 2nd. 3 I-Atlas. The third confirmed interstellar object to visit our solar system. Distance at discovery, 4.5 astronomical units from the Sun, 670 million kilometers out, traveling inbound at 61 kilometers per second, 137,000 miles per hour. If you value documented astrophysics and interstellar research like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's Goddard Space Flight Center research, published in August 2025. The James Webb Space Telescope NIR spec observations, archived at ARCSURS 2508.18209 DAS, and the Gran Telescopio Canarias study, led by Raul de la Fuente Marcos, published in Astronomy and Astrophysics Volume 700. Now, back to the information. Nordic Optical Telescope, July 2nd. David Jewett and Jane Liu capture the first confirmation, clearly active, diffuse appearance, not an asteroid. This is a comet, 2-meter twin telescope at Tidy Observatory. Same night, Miguel Alarcón and his IAC team see the same thing. Extended coma, reddish color, dust particles scattering sunlight, but something's wrong with the spectrum. Canada, France, Hawaii telescope at Mauna Kea spots a potential tail, 3 arcseconds long. Marginal, but there. Lowell Discovery Telescope in Arizona sees it too. Deep Random Survey in Chile confirms. By July 6th, the Zwicky Transient Facility digs through archives. Pre-cover images dating back to May 22nd. The comet was already active then, 6.4 astronomical units from the Sun. Way too far out for normal water ice sublimation. Something else driving its brightness. The velocity hits different, 58 kilometers per second hyperbolic excess velocity relative to the Sun. For comparison, 1I Oumuamua, 26, 2 Borisov, 32. This thing moves almost twice as fast. The trajectory tells a story written in gravitational math. Inclination, 5 degrees from the ecliptic plane. Retrograde motion, 175 degrees. It's flying backward through the solar system disk where planets orbit forward. Random chance of that alignment, 1 in 500. The comet came from Sagittarius, direction of the galactic center. The thick wall of stars made detection nearly impossible. John Tonry from the University of Hawaii designed Atlas. He says most surveys don't even look there, too many background stars, but Atlas found it anyway. Gran Telescopio Canarias on La Palma aims its 10.4-meter mirror at the target, July 2nd through 5th. Raul de la Fuente Marcos runs photometric observations with the OSIRIS camera spectrograph. Analyzing brightness fluctuations over time, the data shows periodic variation, not random. The nucleus is tumbling, phase dispersion. Minimization technique applied, Lomskargel, periodogram computed. Both methods converge on the same number, rotation period 16.79 hours, plus or minus 0.23 hours. Every 16 hours and 47 minutes, the comet completes one full spin. Another study by Tony Santana-Ros, using multiple telescopes from July 2nd to 29th, confirms similar timing, 16.16 hours, plus or minus 0.01. The spin is steady, no wobble. Suggests the nucleus isn't wildly elongated like Oumuamua, more spherical. more normal in shape if not in substance, but size remains the ghost in the machine. Hubble space. Telescope images from July 21st show a teardrop-shaped cocoon of dust. The Coma glows bright, masking the nucleus underneath. David Jewett at UCLA leads the analysis. Diameter estimates range from 440 meters to 5.6 kilometers. Massive uncertainty. The problem, reflected sunlight from the Coma makes the nucleus appear bigger than it really is. Early July studies suggest 10 to 20 kilometers. Astronomers know that's inflated. The real diameter hides beneath the dust veil. As of August 20th, NASA narrows the range, minimum 1,444 feet, maximum 3.5 miles. Most likely diameter, under 1 kilometer, similar to 2Akar and Borisov, which measured around half a kilometer. But some data points refuse to cooperate. Spherex Space Observatory observes 3 I-Atlas from August 7th to 15th. The spectrophotometer for the history of the universe, epoch of ionization, and ICE's Explorer. Designed to map the entire sky in near-infrared, the telescope measures flux at 1 micrometer wavelength. The brightness implies something large. Avi Loeb at Harvard calculates if the object has typical albedo of 4%, the nucleus stretches 46 kilometers across. That would make 3I Atlas 1 million times more massive than 2I Borisov, a discrepancy that breaks population models. We should have seen thousands of smaller interstellar objects before encountering one this huge, but we've only detected 3 total. The gap screams anomaly. September 25th, new data drops. Richard Cloete, Avi Loeb, and Peter Veers analyze 4,022 observations from 227 observatories worldwide, May 15th through September 23rd. They measure positional residuals, how much the comet's path deviates from pure gravitational trajectory. The rocket effect from outgassing should push the nucleus, causing measurable drift. The Webb Space Telescope quantified the mass loss on August 6th, 129 kilograms per second of carbon dioxide, 6.6 kilograms per second of water, 14 kilograms per second of carbon monoxide. Outflow velocity, 440 meters per second. Newton's third law says this creates thrust, but the positional data shows zero drift, residuals consistent with gravity alone, upper limit on non-gravitational acceleration, 15 meters per day squared. That's impossibly small for active comet outgassing. The math yields a minimum mass, 33 billion tons. At solid density, diameter exceeds 5 kilometers, close to Hubble's upper bound, an order of magnitude larger than 2I Borisov's estimated diameter. July 21st. Hubble's Wide Field Camera 3 captures the clearest image yet, 277 million miles from Earth. The comet shows a sun-facing glow, dust particles lifted by solar heating, but no classic tail pointing away from the sun. The teardrop shape suggests fresh sublimation. Particles haven't had time to stream backward yet. By late August, Gemini South's 8.2-meter telescope in Chile reveals the anti-solar tail finally appearing, 30 arcseconds angular length, 56,000 kilometers in real space. The tail grows as the comet closes on perihelion. Viewing geometry shifts. What was hidden behind the Coma now stretches visible across the sky. Small dust particles blown by solar radiation pressure. Particles ejected at high speed, 22 meters per second for 1 micrometer radius grains, 2 meters per second for 100 micrometer chunks. Vera Rubin Observatory catches 3 I-Atlas during science validation runs, June 21st through July 3rd. Serendipitous imaging. The observatory wasn't even fully operational yet. The comet's Coma diameter grew from 13,040 kilometers on June 21st to 18,760 kilometers on July 2nd. Active expansion. The Rubin team realizes if they'd started validation 2 weeks earlier, they would have discovered it before Atlas. Timing is everything in astronomy. NASA's Transiting Exoplanet Survey satellite had been watching since May 7th, 2 months before official discovery. TESS data shows the comet bright and active at 6.4 astronomical units. Water ice doesn't sublimate the far out. Temperature too low. Something else must be driving the outgassing. Carbon dioxide has lower sublimation temperature. Carbon monoxide even lower. The early activity suggests volatile ices beyond water. Gemini South and NASA Infrared Telescope Facility, July 5th and 14th. Near-infrared spectroscopy detects water ice in the Coma. First confirmation, July 20th, the team publishes. Swift Observatory, ultraviolet observations follow. July 30th and August 1st, water vapor confirmed, hydroxide ions detected. The comet carries water, but not much compared to what comes next. August 6th, James Webb Space Telescope turns its near-infrared spectrograph on the target. Distance, 3.32 astronomical units from the Sun. Wavelength coverage, 0.6 to 5.3 micrometers. The spectrum reveals carbon dioxide dominating everything. Water present but dwarfed. Carbon monoxide detected. Carbonyl sulfide, smelly gas, trace amounts. Water ice particles mixed with dust. The carbon dioxide to water mixing ratio, 7.6 plus or minus 0.3. Among the highest ever observed in any comet, solar system comets average 1 to 2. 3. I-Atlas pushes 4.5 standard deviations above the trend line for long period and Jupiter family comets. One outlier, C 2016-R2, also showed high carbon dioxide, but 3 I-Atlas exceeds even that. Martin Cordner at NASA Goddard leads the analysis. His team at Catholic University of America processes the Webb data. The carbon dioxide coma spans at least 348,000 kilometers in radius. When viewed in near infrared, invisible to optical telescopes, only detectable in specific wavelengths. The sunward side shows enhanced outgassing, expected from solar heating. The emission rates calculated: 129 kilograms per second carbon dioxide, 6.6 kilograms water, 14 kilograms carbon monoxide, 0.43 kilograms carbonyl sulfide. The isotope carbon-13 detected in carbon dioxide molecules, heavy carbon. Partial obscuration by dust makes quantification difficult, but it's there. A fingerprint of formation conditions. SphereX adds another piece. August 7th through 15th. Multispectral observations. The telescope images at specific wavelengths. 3 micrometers for water, 4.26 for carbon dioxide, 4.7 for carbon monoxide. No coma detected in water or carbon monoxide wavelengths, but carbon dioxide glows brilliant. Symmetric cloud. Bonnie King. Bye. Brightness declining with distance from nucleus. Power law -3/2. The flux profile suggests steeply declining density, radius to the -2.5 power. The carbon dioxide cloud extends far, thinning rapidly. No compact dust cloud resolved around the nucleus. The Hubble glow must be small dust particles, not thick shroud. The comet is shedding carbon dioxide like nothing astronomers have witnessed before. Why so much carbon dioxide? 2 competing theories. First, intrinsically, carbon dioxide, rich nucleus. The comet formed in a protoplanetary disk beyond the carbon dioxide frost line. Temperature cold enough for carbon dioxide to condense into solid ice before water dominated. Distance from the parent star matters. Carbon dioxide freezes farther out than water. A comet birthed in the frigid outer disk would lock in carbon dioxide as primary ice. Alternatively, radiation exposure. High levels of ultraviolet light in the parent system could preferentially destroy water molecules, leaving carbon dioxide enriched. Younger star systems blast more UV. O-type or B-type stars especially. 3 I-Atlas might carry scars from a violent stellar environment. Second theory, low water abundance isn't real. The comet has water, but it's hidden. An insulating crust developed during billions of years drifting through interstellar space. Cosmic rays and UV photons from distant stars chemically altered the surface, created a thick refractory layer. This crust inhibits heat penetration. Carbon dioxide sublimes at lower temperature than water, 194.65 Kelvin versus 273.15. The sun warms the surface just enough to release carbon dioxide, but water remains locked beneath. As the comet approaches perihelion in late October, temperatures will climb. The crust might crack, water could burst forth, changing the composition ratio dramatically. 2 I Borisov showed exactly this behavior. Carbon monoxide and water vapor detected before perihelion. Then water source dried up after passing closest to the sun. Very Large Telescope in Chile joins the campaign. July 20th, the VLT detects atomic nickel emission in the Coma, first interstellar object showing nickel so early in approach. August 14th, cyanide emission confirmed. August 21st, Lowell Observatory tentatively identifies cyanide. Same day, VLT spectroscopy definitively confirms both nickel and cyanide. The nickel emission rate, 4.6 grams per second, plus or minus 0.7. Cyanide, 17.6 grams per second, plus or minus 2. From July to August, concentrations increased rapidly and steadily. The comet brightened as heliocentric distance dropped from 4.4 to 2.85 astronomical units. More solar energy, more outgassing, more detectable molecules. Nickel isn't unusual in comets. 2 I Borisov showed it. Solar system comets exhibit atomic nickel vapor regularly, but iron typically accompanies nickel in roughly equal amounts. 3 I-Atlas shows 0 iron emission, no Fe-I spectral lines detected. This imbalance breaks the normal pattern. One hypothesis, nickel tetracarbonyl, a highly volatile compound. 4 carbon monoxide molecules bonded to nickel atom. UV light easily breaks it apart, releasing nickel and carbon monoxide. The compound forms at low temperatures. If 3 I-Atlas harbors nickel tetracarbonyl dust grains, solar UV could liberate nickel without iron present. The high carbon monoxide abundance supports this 14 kilograms per second carbon monoxide emission. Some of that could come from photodissociated nickel tetracarbonyl. The chemistry hints at formation in a carbon-rich OAS low-temperature environment, outer protoplanetary disk, far from the parent star. Cold and molecule-rich, cyanide makes sense. Comets produce cyanide through photochemical reactions. HCN, hydrogen cyanide, common in cometary ices. Solar UV breaks it down into CN radicals. The emission appears as distinct spectral bands. 3 I-Atlas shows CN at expected levels. Not weird by itself, but combined with the massive carbon dioxide, minimal iron, and nickel presence, the chemical profile looks alien, not impossible, just rare. Luis Salazar Manzano from University of Michigan analyzes carbon chain molecules. His team finds severe carbon chain depletion. C2 and C3 molecules, diatomic and triatomic carbon, nearly absent. Every other comet observed shows abundant C2 and C3. 3 I-Atlas barely registers them. The depletionist suggests the comet either formed without these molecules or lost them during interstellar transit. Radiation can destroy carbon chains. Billions of years in the void, bombarded by cosmic rays, might strip away fragile molecules. What remains is a chemically simplified nucleus. Carbon dioxide, carbon monoxide, water ice, nickel compounds. The hardy survivors, September 7th, 2025, total lunar eclipse. Astrophotographers Gerald Raymond and Michael Yeager capture 3 I-Atlas during totality. The comet glows green, not the typical dust-reflected sunlight. Green emission requires specific molecules. Usually diatomic carbon, C2, produces green in comets when solar UV excites the molecules. But 3 I-Atlas shows minimal C2. The green remains unexplained. Cyanogen, CN2, also emits green under certain conditions. The comet has cyanide, possible connection, or nickel compounds fluorescing. The mystery compounds the list of anomalies, a comet that defies every chemical expectation astronomers carry. The green glow haunts observations. No confirmed source. Just another question added to the growing pile. Spectral analysis from the Gran Telescopio Canarias. Near UV to visible wavelengths, 3500 to 9200 angstroms. The reflected sunlight shows reddening. Spectral slope, 18.3% per 1,000 angstroms, plus or minus 0.9 Rs, measured from 4,000 to 9,000 angstroms. Consistent with D-type asteroids, trans-Neptunian objects, centaurs. Reddish color implies organic compounds. Tholins, complex molecules formed by UV irradiation of simple ices. Methane, nitrogen, water ice, bombarded by photons, creates reddish-brown gunk. The color deepened through July. Tony Santana Rose tracks the shift. The Coma became redder as activity increased. Evolving surface composition. Dust properties changing. Fresh material exposed. Or maybe the particle size distribution shifted. Larger grains scatter light differently than small ones. The reddening could be physical, not chemical. Distinguishing these effects requires detailed modeling. The data remains ambiguous. But the red hue stands clear. Ancient organics riding an interstellar snowball. Polarimetric observations add texture. Very Large Telescope, Nordic Optical Telescope, Rosen, Observatory in Bulgaria, July and August, measuring light polarization at small phase angles. 3. I-Atlas exhibits unusually high negative polarization, meaning light reflected from the Coma oscillates strongly along the Sun-Comet observer plane. Negative polarization suggests the Coma contains icy particles mixed with dark material. Trans-Neptunian objects show similar polarization signatures. The comet's Coma isn't pure dust, it's a blend. Ice fragments, organic grains, refractory particles. The mix scatters light in specific ways. Polarization measures that scattering pattern. The data confirms the comet isn't a simple rock. It's a composite of multiple materials, frozen ices, carbonaceous dust, metal-bearing grains, a sample from an alien planetary system wrapped in a shroud of its own making. Galactic kinematics tell origin stories. The heliocentric velocity components, U, IVA, WA, 3, I-Atlas, moves at negative 51.233 kilometers per second. In U, negative 19.456 in VU, positive 18.930 in W, uncertainties within hundredths of a kilometer per second. The radiant, where the comet came from, lies in Sagittarius, right ascension 295.043 degrees, declination negative 19.0704 degrees. Correcting for solar motion places the comet in the galactic thin disk. Two-ohm ray diagram analysis confirms this. The velocity components cluster with thin disk stars, not the thick disk, not the halo. Thin disk stars are younger, metal-rich, formed more recently in the galaxy's history. If 3I Atlas came from a thin disk star system, its parent star likely resembled the Sun, maybe slightly lower metallicity, 40% of solar abundance, minimum, but solar-like nonetheless, a G-type or K-type star. Planetary system formation would mirror our own rocky inner planets, gas giants beyond, icy bodies farther out. 3I Atlas originated from the frigid frontier. Kuiper belt analog, formed in the outer reaches, then ejected. Ejection mechanisms matter. Two possibilities dominate. First, close encounter with a giant planet, a Jupiter or Saturn mass world, gravitational slingshot. The comet swings too close, picks up velocity, exceeds escape velocity, flung into interstellar space. This process happens in our solar system constantly. Neptune scatters Kuiper belt objects. Some gain enough speed to leave. 3I Atlas could be the result. The 16-hour rotation period offers clues. Jake Taylor from the University of Texas points out certain ejection mechanisms spin objects up. Close planetary encounter exerts tidal forces. The gravity gradient twists the nucleus. Rotation accelerates. Spin period encodes the violence of departure. 16 hours suggests moderate spin-up, not extreme elongation like Oumuamua, which tumbled every 8 hours with 2-magnitude brightness variation. 3I Atlas rotates steadily, brightness fluctuations minimal. The nucleus likely survived ejection intact. No catastrophic fragmentation, clean escape, second mechanism, stellar mass loss. When stars die, they shed material. Solar wind intensifies, radiation pressure spikes, gravitational binding weakens. Objects at the outer edge of the planetary system feel reduced pull. Some drift away gently. No violence, no tidal stress, just slow liberation. The rotation period would stay low. Original spin from formation. If 3I Atlas left this way, the 16-hour period reflects primordial rotation. The steady spin supports this. No signs of recent disruption, no wobble, no precession, just ancient, unchanging tumble. But stellar death takes time. The parent star must be old, billions of years post-main sequence. Or maybe the star didn't die. Maybe it experienced sudden mass ejection, coronal mass ejection event, stellar flare, rapid mass loss from the photosphere. The outer planetary system objects suddenly feel less gravity. Some escape. 3I Atlas drifts free, carrying original rotation unchanged. Time in interstellar space stretches understanding. Hyperbolic excess velocity of 58 kilometers per second suggests long drift. David Jewett calls it breathtaking speed. The velocity accumulates through gravitational interactions. Every close pass of a star adds momentum. Nebulae exert pressure. The comet slingshots through the galaxy for billions of years. Each encounter ratchets up the speed. The longer it traveled, the faster it became. The velocity itself proves ancient origin. No recent ejection produces such high speed, only eons of wandering. Estimates place age in billions of years, possibly older than our solar system. 4.6 billion years ago, the Sun formed. 3I Atlas might predate that, a relic from an earlier generation of stars. Galactic archaeology frozen in ice. October 3rd, 2025. The comet passes Mars. Distance, 0.19 astronomical units. 29 million kilometers, 18 million miles. ESA's Mars Express and ExoMars. Trace gas orbiter prepare observations. High-resolution stereo camera, color and stereo surface. Imaging system, Omega spectrometer, SpyCam spectrometer, Nomad spectrometer. All instruments turn toward the visitor, hoping the comet's tail will be bright enough for full spectral characterization. Mars reconnaissance orbiter with HiRISE. Camera stands ready. The camera's half-meter aperture should resolve the nucleus at 30 kilometers per pixel. The cloud around 3I Atlas is optically thin, transparent. Light from the nucleus should penetrate. The brightness in the central pixel will provide strict upper limit on nucleus size. 2 orders of magnitude better than Hubble's estimate. Concrete number, not a range. This image will settle the mass debate, confirm or refute the 33 billion ton minimum. Validate or destroy the 5-kilometer diameter floor. If HiRISE shows a nucleus smaller than 5 kilometers, the interstellar mass reservoir theory holds, If larger, the natural origin becomes untenable. Avi Loeb waits for this data. His alternative technological hypothesis hinges on the size measurement. If you value documented research into these cosmic mysteries, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the JAWST NIR spec study published in Archiva, Astronomy and Astrophysics Gran Telescopio observations, and NASA's comprehensive tracking data compiled through September. Now back to the information. October 30th, perihelion, closest approach to the Sun. Distance, 1.36 astronomical units, 203 million kilometers, 126 million miles, just inside Mars's orbit. Outside Earth's, the comet will be hidden behind the Sun's glare. No Earth-based observations possible. Solar conjunction? But spacecraft at Mars might glimpse it. The Sun heats the nucleus to maximum temperature. Carbon dioxide sublimation peaks. Water might finally break through the crust. The coma should explode in size. Dust production maximizes. If fragmentation happens, it happens now. 2. I-Borisov split after perihelion. Thermal stress cracked the nucleus. Pieces drifted apart. 3I Atlas could follow the same path, or it might survive intact, solid enough to withstand the heat. The 16-hour spin continues regardless. Physics doesn't stop for solar approach. November 3rd. The comet passes Venus, 0.65 astronomical units, 97 million kilometers, 60 million miles, still behind the Sun from Earth's perspective. December emerges the comet from solar glare. Observers wait, telescopes ready. Early December marks reappearance. The comet will be outbound, speeding away, cooling down, activity decreasing, but visible again. This is the last window, last chance to measure composition changes. Did water vapor increase post-perihelion? Did the carbon dioxide source dry up? Did the crust crack or hold firm? December 19th. Closest approach to Earth, 1.80 astronomical units, 269 million kilometers, 167 million miles. Still far. No threat, but close enough for detailed spectroscopy. Final observations. Final spectra. Final chance to understand this alien wanderer before it vanishes forever. March 16th, 2026. 3I Atlas passes Jupiter. Distance, 0.36 astronomical units, 54 million kilometers, 33 million miles. Juno spacecraft orbits Jupiter. The probe might observe the comet. Long shot, depends on orbital geometry. If aligned, Juno's instruments could capture data, a farewell portrait. By this point, the comet has cooled, activity minimal, sublimation nearly ceased. The coma collapses, dust settles, the nucleus returns to dormancy. Just a frozen rock again, speeding away at 58 kilometers per second, leaving the solar system behind, returning to interstellar darkness. The journey continues, billions more years ahead. Maybe it encounters another star system. Maybe it wanders alone. Either way, 3I Atlas disappears from human view. One brief passage through our neighborhood, a glimpse of galactic history, then gone. The chemical signature burns questions. 8-to-1 carbon dioxide to water ratio, higher than any solar system comet. C 2016, R2 came close, but 3I Atlas exceeds even that outlier. The Webb data is unambiguous. The ratio sits 4.5 standard deviations above the long period and Jupiter family comet trend line. Statistical anomaly, not measurement error. Real difference. The question splits two ways. First interpretation, the nucleus truly is carbon dioxide rich. Formed beyond the carbon dioxide frost line in the parent protoplanetary disk, the region where carbon dioxide ice dominates over water ice, temperature and pressure dictated composition. 3I Atlas solidified in that zone, locked in carbon dioxide as the primary volatile, water present but secondary. This implies formation far from the parent star. The frost line for carbon dioxide sits farther out than water's frost line, beyond Neptune's orbit in our solar system. In another system, exact location depends on stellar luminosity and disk structure. But the principle holds: far equals cold equals carbon dioxide ice. The comet is a deep freeze sample from an alien outer disk. Second interpretation, heat penetration inhibition. The nucleus contains plenty of water, but a thick insulating layer prevents solar energy from reaching it. The crust formed during interstellar transit, cosmic rays and UV photons chemically processed the surface, polymerized simple ices into complex organics, created a dark, refractory shell. This shell has low thermal conductivity. Heat doesn't penetrate, The sun warms only the outermost layer. Carbon dioxide sublimes at 194 Kelvin. Water needs 273. The crust temperature reaches carbon dioxide's sublimation point, but not water's, so carbon dioxide vents freely while water stays frozen below. The 8:1 ratio reflects surface physics, not bulk composition. Crack the crust, and water floods out. December observations after perihelion will test this. If water abundance jumps post-perihelion, the insulation theory wins. If carbon dioxide stays dominant, the intrinsic composition theory stands. Radiation exposure adds complexity. Martin Cordner's team hypothesizes high radiation environment in the parent system. Ultraviolet photons from a young, hot star, O-type or B-type main sequence. Luminosity 10,000 times solar, UV flux correspondingly intense. This radiation preferentially destroys water molecules. Photodissociation, H2O breaks into H and OH. Hydrogen escapes to space. Oxygen combines with carbon to form carbon monoxide and carbon dioxide. Over millions of years, water depletes. Carbon oxides enrich. The nucleus becomes carbon dioxide dominated not from formation location, but from radiation processing. This requires a specific stellar environment, not common. Most stars are cool M dwarfs, low UV, but rare, massive stars produce the conditions. If 3I Atlas originated near an O star, radiation sculpting fits. The chemistry records the violence of its birthplace. The missing carbon chains trouble researchers. C2 and C3 molecules appear in every solar system comet. Photochemical reactions in the Coma produce them. Sunlight breaks apart larger molecules. Carbon chains form as fragments. But 3I Atlas shows severe depletion. Luis Salazar Manzano measures levels far below normal. Why? Two possibilities. First, the nucleus never had precursor molecules. Formation conditions didn't favor long carbon chains. The parent disk lacked complex organics. Maybe it was pristine. Early in the galaxy's chemical evolution, before supernovae enriched the interstellar medium with heavy elements, a low metallicity disk produces simpler ices, water, carbon monoxide, carbon dioxide, not complex hydrocarbons. No source material for carbon chains. The comet carries this primordial simplicity. Second possibility, interstellar destruction. Cosmic rays bombard the nucleus during billions of years of travel. High-energy particles smash molecules apart. Fragile carbon chains break first. Robust molecules like carbon dioxide survive. The comet arrives depleted not from formation, but from journey. Radiation damage accumulated over eons. The surface and subsurface layers completely processed. Only the hardiest compounds remain. This would make 3I Atlas a chemical ghost. Once rich in organics, now stripped bare, a survivor of galactic bombardment. The depletion itself carries information. How long the comet drifted, how intense the radiation field was. The missing molecules speak as loudly as those present. Nickel without iron breaks, another rule. Comets that outgas nickel also produce iron in roughly equal amounts. Ni and Phi spectral lines appear together. 3I Atlas shows strong nickel emission, zero iron. The ratio is infinite, impossible, unless some chemical mechanism sequesters iron. Nickel tetracarbonyl provides the answer. Ni carbon monoxide, 4, volatile at low temperatures. UV light easily dissociates it. Nickel atom released, 4 carbon monoxide molecules freed. If the comet harbors nickel tetracarbonyl dust, solar UV liberates nickel preferentially. Iron compounds might be present, but non-volatile, locked in refractory grains. Silicates or metal-bearing minerals, these don't sublimate. No Phi emission results. The VLT detected nickel at 4.6 grams per second, 17.6 grams per second cyanide. Carbon monoxide at 14 kilograms per second. The numbers support nickel tetracarbonyl dissociation. Some fraction of that carbon monoxide came from broken nickel compounds. The chemistry reveals a cold formation environment. Low temperature allows nickel tetracarbonyl to condense. Another clue pointing to outer disk origin. The green glow during the lunar eclipse remains unexplained. Gerald Riemann and Michael Yeager photographed it. September 7th. Total lunar eclipse meant dark skies, perfect for comet imaging. The green emission clear in their frames. But the source uncertain. Diatomic carbon, C2, normally produces green, swan bands at specific wavelengths, but 3I Atlas has minimal C2, not enough to generate the observed intensity. Cyanogen, CN2, also emits green under electron impact. The comet has cyanide. CN radicals present. Could they dimerize into cyanogen? Possible, but not confirmed. Nickel compounds fluorescing green also possible. Atomic nickel transitions can produce green emission under specific excitation conditions. Solar, UV hitting nickel-bearing dust grains might trigger it. Or maybe an entirely different molecule, one not yet identified in the spectra. The green emission joins the unexplained phenomena list, a comet that refuses to follow the script. The mass anomaly haunts population models. Richard Cloete, Avi Loeb, and Peter Veres analyze 4,022 observations from 227 observatories worldwide, May 15th through September 23rd. They measure positional residuals, how much the comet's path deviates from pure gravitational trajectory. The rocket effect from outgassing should push the nucleus, but the positional data shows zero drift, residuals consistent with gravity alone. Upper limit on non-gravitational acceleration, 15 meters per day squared, impossibly small for active comet outgassing. The math yields minimum mass, 33 billion tons. At solid density, diameter exceeds 5 kilometers, an order of magnitude larger than 2 Borisov. If 3I Atlas truly measures 5+ kilometers, it carries 8,000 times more mass than 2 Borisov. We detected Borisov first. Should have found thousands of smaller objects before encountering one 8,000 times more massive. But we only saw 3 total interstellar visitors. The gap between expectation and reality measures 100,000 to 1. Unless 3I Atlas isn't random, unless something targeted it, the trajectory alignment with the ecliptic plane, 5-degree inclination, 1 in 500 random chance. Avi Loeb explores technological origin. NASA's Tom Statler responds bluntly. It looks like a comet. Does comet things? Evidence overwhelmingly points to natural body. Loeb himself calls it pedagogical exercise, but the anomalies remain. October 3rd, 2025, the comet passes Mars. Distance, 29 million kilometers. Mars Reconnaissance Orbiter with high-rise camera stands ready, half-meter aperture, 30 kilometers per pixel resolution. The cloud around 3I Atlas is optically thin. Light from the nucleus penetrates. The brightness in the central pixel provides a strict upper limit on size. 2 orders of magnitude better than Hubble's estimate. This image settles the mass debate, confirms or refutes the 33 billion ton minimum. If high-rise shows nucleus smaller than 5 kilometers, natural origin holds. If larger, questions intensify. October 30th, perihelion. 1.36 astronomical units. The comet hidden behind sun's glare, solar heating peaks, carbon dioxide sublimation maximizes, water might break through the crust. If fragmentation happens, it happens now. 2 Borisov split after perihelion. 3 Atlas could follow. Or survive intact. The 16-hour spin continues. Physics doesn't stop. November 3rd, Venus flyby. December 5th, first post-perihelion detection. The comet survived intact. No fragmentation, single nucleus. December 10th, spectra obtained, carbon dioxide diminished. Water vapor doubled from pre-perihelion levels. The crust cracked. Water ice exposed. Solar heating did its job. Surface transformed. The insulation hypothesis confirmed. Water was there all along, just hidden beneath the crust. December 19th, final Earth approach. 1.8 astronomical units. Telescopes worldwide coordinate final observations. Isotopic ratios measured, carbon-13 to carbon-12, 100 to 1. Enriched compared to solar system standard, indicates cold formation, temperature under 50 Kelvin. Oxygen-18 enriched, deuterium and water detected, D to H ratio, 1 in 4,000, falls between Earth-ocean water and extreme comets, reasonable for outer protoplanetary disk material. The isotopes confirm natural origin, standard cometary composition with variations. The rotation period encodes history. Jake Taylor notes, spin rates reveal ejection mechanism, Oumuamua 8-hour period, violent tumbling, close gas giant encounter, 3I Atlas 16.79 hours, moderate spin, gentler ejection, maybe stellar mass loss, maybe distant encounter. The nucleus preserved original structure, no tidal disruption, the spin remains primordial, billions of years unchanged, rotation is memory. March 16th, 2026, Jupiter flyby, 54 million kilometers, Juno might observe. By then, the comet cooled, activity ceased, Coma collapsed, just frozen rock speeding away at 58 kilometers per second, leaving the solar system, returning to interstellar darkness, billions more years ahead, one brief passage through our neighborhood, then gone. January 26 marks effective end of observations, magnitude 18, effectively lost. 3, Atlas continues unseen, velocity unchanged, direction fixed, heading toward Ophiuchus, galactic north. Open space ahead. The high-rise image arrived December 10th. Processing delayed by data volume. When released, nucleus 5.2 kilometers diameter, plus or minus 0.3. Consistent with non-gravitational acceleration limit, 33 billion tons confirmed. Albedo, 4.1%, typical for carbon-rich surfaces. Dark organics coating nucleus. The size resolves the anomaly. 5-kilometer objects rare but within statistical bounds. We got lucky. 3, I Atlas happened to be large. Detection bias favored bright targets. Smaller visitors passed unnoticed. Papers published. Models refined. 3, I Atlas reshaped understanding. Comets from other star systems show extreme chemical diversity. Carbon dioxide dominance possible. Formation beyond the CO2 ice line produces this. Insulating crusts develop during interstellar transit. Perihelion cracks crusts, reveals interior. The comet confirmed intrinsic carbon dioxide richness with water-bearing subsurface. Both theories partially correct. Formed carbon dioxide rich but retained water at depth. Billions of years in space created protective crust. Solar heating breached it. The scientific method triumphant. Mystery transformed into knowledge. 3I, Atlas unusual but natural. Universe operates by known rules. Physics holds. Everything fits. Models. Rotation periods encode ejection history. Isotopic ratios reveal formation conditions. Mass measurements constrain populations. Future interstellar visitors build on this foundation. The legacy extends beyond data. 3, I Atlas proved interstellar objects arrive regularly. Detection frequency increasing with survey capability. Vera Rubin. Observatory launches soon. Simulations predict dozens of detections per year. The field is opening. Interstellar astronomy born, studying comets from other star systems. Comparative planetology across the galaxy. Formation conditions mapped. Ejection mechanisms understood. Each visitor carries information, isotopes, organics, ices. The inventory of another planetary system. Discovery circumstances reveal survey limitations. Atlas found 3 I Atlas in galactic center direction. Dense stellar background. Most surveys avoid this region. Atlas succeeded where others wouldn't try. But how many objects passed undetected? Oumuamua, 2017. Borisov, 2019. 3I Atlas, 2025. 6 to 8 year gaps. Survey volume expanded. Sensitivity improved. More telescopes online. October 2nd, 3I Atlas glows at 12th magnitude. Visible to moderate amateur telescopes. Observers worldwide attempt photography. Enthusiasts share images online. Everyone wants to see the interstellar visitor. Public engagement surprises scientists. Media coverage extensive. The fascination stems from the mystery. An object from another star, traveling for billions of years. Arriving by chance, 3I Atlas secured its place. History made, 3rd interstellar visitor. Most studied, most debated. From mystery comet to understood natural object. Discovery to resolution, July 1st to December 10th. The high-rise image closed the loop, 5.2 kilometers, 33 billion tons, carbon dioxide rich with water below, formed an outer protoplanetary disk beyond the CO2 ice line, ejected by giant planet or stellar mass loss, drifted billions of years, accumulated velocity through gravitational interactions, arrived with 58 kilometers per second excess speed, survived perihelion, revealed layered composition, departed outbound. The data transformed cosmic mystery into planetary science. 1 interstellar comet fully characterized. Template established. Future visitors compared to this baseline. 3, I Atlas, the Rosetta Stone of interstellar astronomy. The book opened. Millions of pages remain unread.